All right, welcome back. We are nearing the end of our final unit together. This is section 8.3, and we are talking about what is known as the dot product. There's a couple of learning targets for this section. Um, Both have to do with using formulas that we're going to derive, but they both rely on something called the dot product. So in 8.1, we talked about different operations that we could perform on vectors, including adding and subtracting them and multiplying by a scalar. But we didn't really talk about what it means to multiply two vectors together. There's a couple of ways we can think about doing this, and one of those is known as the dot product. So basically, dot product, and we write it as like literally a dot in between our two vector names. U dot v is how we pronounce it. Equals, we multiply the two horizontal components together, and then we add the two vertical components together, or add the product of the two vertical components. So notice that when we do this, we don't end up with a vector. We end up with a number, a scalar. So in case you'll forget, I made sure to put it nice and bold, underlined, all caps, and a much bigger font. The dot product is a scalar. It is not a vector. So when we multiply, if you want to think about the dot product as multiplying these two vectors together, we end up with a scalar instead of a vector. Okay, that's important. Because there's certain things we can only do with scalars and certain things we can only do with vectors. So let's start by just going through a bit of practice. How do we calculate the dot product? Again, I always think it's useful to label everything. So U is A1, B1, and V is A2, B2. So finding the dot product, U dot V, that's going to be the two A's multiplied together, and then we'll add the two B's multiplied together. I'm not sure what that was supposed to be, sorry. And 3 times 4 is 12, negative 2 times 5 is negative 10. So in this case, the dot product between these two vectors is simply 2. So really, that's all. That's how we calculate dot product in general. Go ahead and try example 2 on your own. It shouldn't take you all that long. Now, I want to move on to some more interesting uses of the dot product. So the dot product we can think of as having a physical meaning to it, and it's going to take us a couple formulas to get to what that meaning is. But basically, and I will go through this derivation in class for you, so I don't want to extend this video any longer than usual so that you're more likely to watch it. But we see that we can derive what is called the dot product theorem. So if I have two vectors and I know the angle between those two vectors, then we find that the dot product, in addition to being a1, a2 plus b1, b2, is also the product of the magnitudes of the vectors and the cosine of that angle between them. So u dot v equals the magnitude of u times the magnitude of v times the cosine of the angle between u and v. And this is really useful because, all right, maybe we think that our original formula is a little easier for calculating the actual dot product. We can take this formula here, solve for cosine of theta, and we get this really nice formula to calculate the angle between two vectors. Now, the angle between two vectors is something that we use all the time. It's something that we'll often want to find, especially when we move into section 8.4 and that's dealing with applications of vectors. So I think let's just jump in and do an example problem. So find the angle between these vectors, v and u. To do that, we need first to find u dot v, or in this case, we're starting with v. I mean, dot product, the order doesn't matter, but just to keep things consistent, we need the dot product of these two vectors, v dot u. And go ahead and label these. Keep everything organized. So this is going to be negative 7 times negative 1 plus 3 times negative 2, which is 7 minus 6, which is 1. All right, so nice simple dot product. And then we need the magnitude of v. which is going to be the square root of negative 7 squared plus 3 squared, square root of 49 plus 9, or the square root of 58. And then we need the magnitude of u, square root of negative 1 squared plus negative 2 squared, which is the square root of 1 plus 4, which is the square root of 5. So, plugging into our formula, the cosine of the angle between these two vectors, v and u, is going to be the dot product divided by the two magnitudes multiplied together. So we can simplify those radicals, square root of 290, rationalize that denominator, and I don't recognize that from the unit circle, so I'm going to pull out a calculator and take the inverse cosine of square root of 290 over 290. And I'm in degree mode, so I will get an answer in degrees, and I get that the angle between these two vectors is about 86.63 degrees. And that's it. So just take a second and appreciate that. Using nothing other than knowing the vectors, the vertical and horizontal components of each, we're able to calculate the angle between those two vectors. So that's incredibly useful, as we'll see later on. So go ahead and try example 4 on your own. So that's our first learning target for this section, is to be able to calculate the angle between two vectors using this dot product. Another use of the dot product is what we call the component of u along v. So let's explain what this means. So simply put, the component of some vector u along another vector v is the magnitude of the part of vector u that points in the same direction as vector v. And that ends up just being a scalar. It's a number since it's a magnitude. So it's more useful, I think, to look at these pictures. So if I have this vector u and this vector v, okay, the component, in other words, the horizontal or the vertical component of vector u, which would be this right triangle, that is along the vector v, is the magnitude of the part of u that points in the same direction as v. So it's this right here, this part of the in this case, it's the horizontal component of this vector. If we're kind of tilting it and looking at it along 90 degrees. And the same works if they're pointing in opposite directions. It's still the component of u along that vector v. And that is just basic trig, so if this is the side length that I'm looking for, the cosine of that angle in there is going to be whatever that side length is, we can call it x, over the hypotenuse. And it's a length, we need a length, so we need the magnitude. So if I solve for that side length there, I do get magnitude of u times the cosine of theta, the angle between the vectors. So that's incredibly useful as well. Sometimes we want to know what part of a vector is pointing along the same direction as a different vector. Now, if we would rather use the dot product, if, for example, we don't really know that angle between the two vectors, and we don't want to spend the time to figure it out, then let's consider we have magnitude of u times the cosine of theta. Now I can multiply anything by 1, no matter what that 1 looks like, so I'm going to multiply this by the magnitude of v over the magnitude of v. Again, that is 1. Whoops. Again, that is 1. So, simplify this, I get the magnitude of u times the magnitude of v times the cosine of theta all over the magnitude of v. And if you remember our dot product theorem, the dot product, u dot v, equals the magnitudes times the cosine. So this right here becomes the dot product of the two vectors. So we can also think of the component of u along v as u dot v over the magnitude of v. So let's go through an example. We have these two vectors. We want to find the component of u along v, so let's go ahead and use this formula. I need to know u dot v. So that this is a1, b1, this is a2, b2, so this will be 1 times negative 2 plus 4 times 1. Negative 2 plus 4, which is 2. And then the magnitude of v, that is going to be the square root of negative 2 squared plus 1 squared, square root of 4 plus 1, or the square root of 5. So the component of u along v is 2 over the square root of 5. Rationalize that denominator, and this is our answer. So again, physically, what that represents is the magnitude, or the part of vector u that points along the same direction as vector v. Okay? And it is a scalar. It's a length. It's magnitude. It is not a vector itself. So go ahead and try example 6. Okay, I think that'll be useful for you. And if you're still with me, and if not, go ahead and pause, practice, take a second, rewatch any part of my explanation that I've gone through that confused you. I want to take this one step further. So we can talk about that component of u along v. And we can also, right, we said this is a scalar. What if I wanted an actual vector that moves along that component? It points in the same direction as vector v, but it is the magnitude of that component. It has the magnitude of the component of vector u that's in that same direction. So I have this scalar. I have a magnitude. We know that a vector is magnitude and a direction. So we have the scalar, the component, the magnitude, but we need a direction. So how do we get that direction? Well, and just for simplicity, or for clarity's sake, these are some pictures of what I'm talking about. So that same piece that we were talking about for the component, but now it's an actual vector. It has direction. So I still need the component of u along v, but I also need a vector to give it direction. I need a unit vector that points in the same direction as vector v. Because I have a magnitude that I want, so it would be nice if I have a vector that starts with a magnitude of 1, so I can change that magnitude into whatever I need. In this case, it's the magnitude, or the component of u along v. But then I want it to have direction, the same direction as vector v. So that is, in fact, exactly the unit vector that points in the direction of vector v. And if we multiply these two things together, these two formulas that we get, component and then the unit vector, remember, unit vector in a direction of another vector is just dividing that vector by its magnitude, we end up with this pretty simple formula. And we call this the projection of u onto v. So we're actually taking this vector and we're projecting it onto another vector. We're projecting it. It's projection. And we do notate this interestingly. We shorten projection to proj. So it's proj sub v of u. I don't know if anyone actually says that. I feel like I had professors that did, but that sounds weird now that I'm saying it again. And regardless, we end up with a vector, which is what we wanted. So component is a scalar. Projection is a vector. So let's go through an example. We have two vectors, so I'll label them first, of course. And to find the projection of u onto v, we need the dot product, u dot v. And then we will need the magnitude of v. So we need these two things. We'll start with the dot product, multiply the a's together, and then multiply the b's together and add them. We get negative 2 plus 4, which is 2. And then the magnitude of v is 1 squared, square root of 1 squared plus 1 squared, square root of 2. So let's plug all of this into our formula. So the projection of u onto v is u dot v over the magnitude of v squared. And then we multiply that by vector v so that we get that same direction, but we have the right magnitude that we want. U dot v was 2 over square root of 2 squared times vector v, which was 1, 1. Square root of 2 squared is 1. I'm sorry. Square root of 2 squared is 2. 2 over 2 is 1. So in the end, we really just get vector v. In other words, if I take vector u and I project it onto vector v, I just end up with vector v. It does end up being the component of u in the same direction as vector v. So that's really all there is to say about this projection. So this is the second learning target for this section, is being able to compute components and projections. Hopefully I've done a clear enough job of differentiating between the two. Go ahead and try example 8 for yourself, so you have some practice. But in general, I will finish by saying, again, there's no reference sheet for this unit. You don't receive any of these formulas for the final, so you won't receive any of them for our assessments in class, which means you do need to memorize these formulas. There were a few here. Dot product is pretty straightforward. The angle between two vectors, once you use it a few times, I think it'll become a little more ingrained. Component of u along v, and then the projection of u onto v is probably the trickiest formula to memorize, but I have faith in all of you. So let me know if you have questions. Please write them down, bring them to class, to tutoring. We're in our home stretch. Let's get it done. Thank you so much.